Good morning, guys. It's a snow day. I can hear the plow outside, but that doesn't mean we stop doing chemistry. So I'm going to sub in this little video lecture for you on some stuff we would have done together. I'm just going to run the same simulation we watched last time, and now we're going to talk about this in the context of the lab you did where you were trying to increase the temperature of some water in a styrofoam cup by exactly 2 degrees Celsius. So we have to have kind of a mental picture of what the water in the cup looks like before you do anything to it, and then a picture in our heads of what the water should look like after you've successfully raised its temperature. So we played around with this simulation last time, where we're watching these water molecules, and they're in constant motion in this liquid. And they're bashing into each other, and they're hitting the sides of the container. And then we looked, as we raised the temperature, at how things change. Right? So we'll look at that again. We'll take the temperature back down and then raise the temperature back up again. So we talked about how the overall idea is that as we see the temperature rise, what that actually means at the particle level is that the particles, the molecules in this case, are speeding up overall. The picture just looks faster. The bouncing is happening faster. The runs that the molecules make in between collisions are happening faster. Everything's just sped up. And that's what we mean by a temperature increase. So now we're going to do a little bit, we will come back in here. And what we're going to do is we're going to try and actually collect some data on that. So I'm trying to use this new technology, and I'm kind of a mess. But what we're going to try and do is we're going to try to graph this out, all right? So if we were to graph the speed of those molecules, so we know that overall the general trend is, okay, colder water, the molecules are moving slower. Hotter water, the molecules are moving faster. So let's try and graph that out. So we're going to just do a very crude graph here. And what we're going to do is we're going to do speed over on the y-axis. And then we're going to basically just kind of, it's going to be a little bit of an untraditional graph. So we're going to say number of molecules. I'm just going to leave it as molecules for right now. So what you're going to imagine is that you jumped into that tank of water and you're sitting there at the submicroscopic level. And as each water molecule goes by, you're timing it. You're going to see how fast it's going. And we're going to then say, sorry, my kid was just distracting me, and I realized that I messed up my axes. All right, so we're going to do number of molecules. This is a mess. And then down here, we're going to do speed. So these are, we're going to do this is fast over here, and this is slow over here, okay? So what we're going to do is as each molecule goes by in our mental image of that simulation, we're just going to time them. And if a molecule goes by and it's going kind of slow, then we're just going to mark a dot on our graph down here. If there's one that's going pretty fast, then we're going to put it over here. And so what we're going to do over time is we're going to start, just timing them, So we've got some fast ones, we've got some slow ones, another slow one, and we're just going to time them. And our speed, so down here we're just, figuring okay, the faster they are, I get a fast one, I put it over there. This one's speed was right here. So I just start kind of stacking them up, right? So, there's a mix. Some of them go by and they're really, really slow. They're way down here. If you watch the simulation again, you'll occasionally catch a molecule that isn't moving at all. It's just sitting still, it might be just wiggling a little bit. And then you get some that are just blowing by you super fast. But you get a lot that are kind of similar speeds, so your piles start to kind of stack up like this. Right, so we get something like that, where we've now timed a whole bunch of molecules that have been passing us by. Some were going pretty slow, some were going pretty fast, and then a lot were kind of in the middle, right? So if you look at our graph now, you can almost kind of see that we've got a little bit of a curve here. That's kind of looking like that if we define our stacks. And each one of our dots represents a particular molecule going a particular speed. So when you get these kind of tall stacks here, that means there's a lot of molecules. There were a lot of molecules you timed that were going that speed. That was a very common speed. this was a pretty common speed as well. This one was a little bit less common. And then we get into the really fast ones, and they're rare. You know, we get like a really zippy one. And same thing out here. We get like some that are slow. And then as we get over here, we get more and more of them. And so we get kind of this smoothed out curve. All right, so, and then if we wanted to, we could do some mathematics here, and we could say, all right, well, what if I wanted to know their average speed, right? So we could calculate like a mean. We would add up all the speeds that you timed for these guys, and then you would take the number of molecules and you would divide by that. And looking at our curve here, we're probably going to get something like this. Like here's the average speed. So this is for our cool water. So this is for cool water. And if you want to impress your friends, you can know what this kind of graph is called. So what we're looking at here is what's called a Boltzmann distribution. It's named after a dude. They almost always are. So this Boltzmann distribution is just asking, like, if you were to time a whole bunch of these molecules and figure out how fast are they each going, and then graph them like we just did, what would that look like? You know, how would they be kind of spread out? So in our cool water, we get a spread from very, very slow to quite fast, and then the average is sort of that middle range where there's a lot of molecules moving at that kind of middle speed. So this is our Boltzmann distribution for cool water. So what I'm going to have you guys do is just pause the video now. And what I want you to think about is if this is the Boltzmann distribution, where we're graphing the speeds of a whole bunch of water molecules in cool water, then I want you to kind of just get a piece of paper and jot down, how would you draw a Boltzmann distribution for water that is hot? So we're going to take this, we're going to imagine this is our graph for cool water. You're going to now draw one. So you can use the same axes, right? So you're going to have number of molecules over on the y-axis. You're going to track their speed on the x-axis. You're going to have slow over here and fast over here. How would your graph look either the same as this Boltzmann distribution, or how would it look different? So pause the video now, and then when we come back, we'll see how yours compares to what I think would be going on. Okay, I'm back, you're back. Hopefully you've kind of gamed out what you think the Boltzmann distribution would look like for the hot water. So let's now zoom down to that submicroscopic level into the hot water, higher temperature, and let's do the same thing. We're going to watch molecules go by. We're going to sit with our little imaginary stopwatch, and we're going to time them as they go by. So if I start doing that, so I'm going to use a different color. I'm going to use red dots this time. And I'm just going to start tracking. Okay, so they're starting to go by. And I'm getting, let's see, okay, like there goes one a little bit slower. There goes one, there's one, there's one that's really slow. There's a pretty quick one. There's a really quick one. Okay, so I'm just going to start, kind of tracking these. So they're going by kind of random. And these are, as these guys are going by, we're just going to track them in real time. Imagine we can see their speeds. Mesmerizing, I know. Okay, so I'm going to go back to just tracing out the Boltzmann distribution for what we had before. So this was our cool water. Kind of traced it like that, looked like a curve like that. And here was our average speed. All right, so now if we go to our Boltzmann distribution for the hot water, so now, we know the temperature's higher, it's hotter water. We knew that the overall picture was that things just looked faster in the hot water. But now if we trace out, so now we've timed a whole bunch of water molecules that were going by us in the hot water, and we just kind of made a dot for their speed. So slow ones are over on the left side of the axis over here, fast ones are over here, and middle ones are kind of in the middle over here. So when we make a Boltzmann distribution for these guys, and I kind of curve it out here. Now I've made some slight errors, but I'm trying to give you guys a general sense. We look at the Boltzmann distribution here. We've got a curve again, but I want you to pay attention to a few different things. So when you drew a Boltzmann distribution, what I would wonder, and if we were in class together, I would have, asked you about these things together, how yours looks different from mine. And there may be errors in mine, but overall what I've got here is I've still got some really slow ones. So I still have some molecules that were almost not moving in the picture, even when it was sped up, even when it was hot water. So there's always going to be some really slow guys. And we can talk about why that is, why some molecules just aren't moving very fast, even when the overall picture is fast. But then the difference between my two Boltzmann distributions is over here I've got some very fast guys, and in my cool water, the fastest one I had, so I'll go back to this color. Let's see, so that was the fastest molecule that I measured in the cool water. And now if I go back to our hotter water, the fastest one that I have are over here. So we've shifted the whole curve over towards these fast guys, because now there are faster ones. The maximum speed you get in hot water is higher than the maximum speed you get in the cool water. Now, the other thing that we need to look at is that average speed, right? So we know there's faster guys in the hot water than there were in the cool water. There's still slow guys, so there's still really slow guys, but the whole curve is shifted towards the right. So now we've got right here, so this is going to be our average speed for hot water. And then we're just going to label what the top of our Boltzmann distribution over here was, average speed for cool water. So now we've got two Boltzmann distributions, and we see how they're kind of shifted near each other. And even though they both end up starting over here at the same point, because there's always some really slow guys, we see that in the simulation, as you get hotter and hotter water, you're going to have these faster guys over here in this range that were not present in our cooler water. So when you think about your experiment where you were trying to get the water in your styrofoam cup to increase its temperature by 2 degrees, what you're looking at is the difference between these two things. So we've got our average speed of the cool water and our average speed of the hot water. So this is your temperature increase. Because what temperature is actually measuring is the average speed of the molecules, the average kinetic energy. Now, there's a difference between speed and kinetic energy, so I don't want you to necessarily draw a clear line between those in your head. But for our purposes, if you're taking cool water and you're trying to increase its temperature by 2 degrees, what we're saying is we want to take those water molecules and we want to speed them up. And the way we're going to know that they've sped up is by taking their temperature. So for our purposes in this experiment, our thermometer was kind of a speedometer. We're putting it in there and we're saying, okay, water molecules, you started out at 18 degrees Celsius. I want to boost your speed. I want to boost the average speed in there so that on average, those molecules are going 2 degrees faster. You can kind of think about it in that respect. So what we're going to do now is we're going to now look at how you guys accomplished that and what the factors seem to be in trying to get that speed increase to happen. How do you get those water molecules to go from kind of like, we're moving around, but we're not moving super fast, to kind of goosing them and getting them to move. Now, not every single one, because you're still going to have some that are slow from time to time. They're just going to be moseying along. But the average speed, we want the average speed to come up so that on average, the whole picture is faster. The whole picture is 2 degrees Celsius faster than it used to be. So we have to imagine at the level of those molecules, how do you make a molecule move faster? And how do you make it so that a lot of them are moving faster? So that on average, they're moving faster. Not just one gets going faster, but you need to get like the whole mass of them moving faster than they were. So that's going to be what I'm going to post next. I'm going to do it in a separate video because this whole process is challenging.